Hi math students, welcome to the channel Learn It with Emmanuel. I'm back and I'm still here for those who are wondering. So in today's video I'm going to be introducing a new topic. It's a topic of vectors in math paper 1. I'm going to explain it in the simplest way possible, and I believe every single person, whether you're new to math or if it's something you didn't naturally love, I still believe that it will make sense for you as you prepare for UNEB exams. So without wasting time, let's introduce vectors in pure mathematics. Alright, so let's start with the topic of vectors. So this is where we are right now in math paper 1. So this is pure mathematics. So we're going to basically be covering this entire section right here. And today's video we're going to be focusing on the introduction of this topic called vectors. Alright, let's start. Alright, vectors. So now there are two types of physical quantities. Now we're going to look at the first one, which we're going to be focusing on in this series, which is a vector quantity. So a vector quantity is a quantity which has both magnitude or size and direction. For example, displacement, we can say 5 kilometers to the north. Then we also have another example of a vector quantity, force. So we can say a force of 10 newtons at 30 degrees angle. Then we can have another example of an acceleration of 9.8 meters per second squared downward. So you can see all these units have both size or magnitude and direction. Now there is another kind which we call a scalar quantity. So a scalar quantity is a quantity which has magnitude but no associated direction. For example, time. Now we know time has no direction. Time, we just say 30 seconds. Another example is temperature. Temperature 36.5 degrees centigrade. Then we also have an example of power. We only say 60 watts. We don't talk about the direction. So I think it actually makes sense. So you can actually see the example, and I hope this actually makes it clear for you. So vector quantities have both magnitude and direction, and scalar quantities only have magnitude but no associated direction. I just wanted to put this up for you so that you actually get an understanding of what we are going to learn. Let's look at vector variables. Now vector variables are variables used to represent vector quantities which have both magnitude or size and direction. Unlike scalar variables that only describe how much of something there is, vector variables also tell you which way the quantity is acting or moving. So we have different characteristics of vector variables. Now vector variables can be represented in bold small letters like A, B, I, J, K, P, so just name it. So this is one of the ways we may label it as we learn. Then we can also label them with underlined small letters, as you can actually see here. Then we can actually have them with arrows on top, as you can actually see right there. Then there is another way we can also have them as capital letters with arrows on top like B, A, or C, E, G. Now, scalar variables can be written in ordinary small letters as K, G, B, T, M. So I just want to just get this so that you can actually just have a basic understanding. Alright, let's look at the representation of a vector. Now, a line may be drawn to represent a vector and an arrow put to indicate the direction of the vector. For example, you can see the line here, and then you can actually see an arrow in the line that represents the direction of the vector. So this moves from point A to point B. Then you can represent the vector as small a underlined. So here we can say the direction of the arrow corresponds to the order of the letters of the vector it represents. Here this is represented as AB, or we can also call it A with an underlined dash. Let's look at two-dimensional vectors. Now in 2 dimensions, a displacement can be represented as xy. So this is the column vector, and this can be represented in the form xi plus y j. So just note this is actually the exact same thing we see right here. It's just that this is the column vector form, and then this is the other form. So where I and j are unit vectors in the x and y directions respectively. As you can see here, we have the x and y axes, then we have I, and then we have the j. So that's actually how we can represent it. Now for example, 4, 7 can be represented as 4i plus 7j. So this vector means that we've moved 4 units in the direction of the x-axis. And then we've moved 7 units in the direction of the y-axis. As you can see here, the x is now being represented by the 4 and the y is being represented by the 7, which makes this make sense. So we've moved 4 units in the direction of the x-axis and 7 units in the direction of the y-axis. So this is just for you to actually get the picture. Then you can also have 3-dimensional vectors. Now in 3 dimensions, a displacement can be represented as x, y, z. So we've actually added a z into the mix. So a column vector x, y, z can be represented in the form xi plus yj plus plus zk, where I, j, and k are unit vectors in the x, y, and z directions respectively. So this is how we can represent it. We have the x, we have the y, and we have the z. So we have j, k, and I. Now for example, if we have 3, 1, negative 2, this can be presented as 3i plus j minus 2k. Why do we have a minus here? It's because we actually have this as a negative. So you can say this vector means that we've moved 3 units in the direction of the x-axis, 1 unit in the direction of the y-axis, and negative 2 units in the direction of the z-axis. Alright, let's look at addition and subtraction of vectors. Now when adding or subtracting 2 vectors, we must add or subtract corresponding components. This means that care must be taken to add or subtract components in the same direction. Suppose we have the vectors a is equal to a1, a2, a3, and b is equal to b1, b2, b3. Then, if we want to add the vectors a plus b, and we have this, so this is a, and then this is b, we can actually add the corresponding components. So we have a1 adding b1, then we have a2 adding the b2, and then a3 adding with the b3. So actually that's how we calculate such numbers. Then when we're dealing with subtraction, we have something like a minus b, we'll also have the corresponding components subtracting each other. So we'll have a1 minus b1, a2 minus b2, and then a3 minus b3. Let's look at some example. For example, if we're given a is equal to negative I plus 2j plus 3k, and b is equal to 4i minus 5j plus 6k, we're being told to determine the values of a plus b and a minus b. So this is an example of 3-dimensional vectors, which we have I, j, and k. So we can actually choose to first represent these in column vector form. So we're going to have a is equal to negative 1, 2, 3. Then we're also going to have b being equal to 4, negative 5, and 6. The reason for the negatives is because you can actually, there's a negative here on the I, then you can actually have a negative in front of the j. So that's why we have a negative 5 right there. So now a plus b shall simply be negative 1 plus 4, 2 minus 5, and then 3 plus 6. Now we have a negative here because a 2 plus a negative is actually the same as 2 minus, and then that's why we have a 2 minus 5. Then the answer shall be 3, negative 3, and 9. That's a column vector of the sum of the 2 vectors. Then for a minus b, we're going to have it this way. Negative 1 minus 4 is going to give us negative 5. 2 plus 5. Now the reason we have 2 plus 5 is 2 minus a negative. This becomes a positive. So that's why I have 2 plus 5 being equal to 7. Then 3 minus 6 is going to be negative 3. And those are the answers. Now let's look at multiplication of vectors. When multiplying 2 vectors, we must multiply corresponding components and add to the product of other corresponding components. Suppose vectors a is equal to a1, a2, a3, and b is equal to b1, b2, b3. Then a times b shall be equal to, this is what we're going to be doing. We're going to have the corresponding components multiplying each other. Then we shall actually be summing up the answers that we actually get from each corresponding components multiplying one another. That's why we have a1 times b1, then we have a2 times b2, and then a3 times b3, and then we need the sum of all the answers. So that's actually how we deal with multiplication. Let's look at a scalar multiple of a vector. Now to find the scalar multiple of a vector, we simply multiply each of its components by a scalar. Suppose A is equal to A1, A2, A3 is a vector and Y is and lambda is a scalar. Then A times a scalar. If this is a scalar, now remember that this can be a scalar. It can be a number, any number. It can be a number like 2. It can be a number like a half. It can be a number like 0.23. So a scalar is basically any number that is actually multiplying the vector. So suppose we have any single number multiplying the vector. This is what we're going to be having. Then we're going to have that scalar multiplying each of the individual components. And also likewise, if we have A dividing any scalar, remember this can be written as A over lambda, which is equal to this vector divided by lambda, because this vector represents the A. Now remember, this can be changed into a multiplication sign, which shall make it 1 over lambda. So we're going to have 1 over lambda times the vector A1, A2, A3. So that's actually how we deal with division. Now of course in this case, the 1 over lambda is going to be multiplying each of the individual components. Alright, let's look at some questions. Now given A is equal to negative I plus 2j plus 3k and B is equal to 4i minus 5j plus 6k, determine the values of 4a plus 3b and negative 3a minus 2b. Now we know that A is equal to negative 1, 2, 3. So we've actually converted this into a column vector form. Then we also have B being equal to 4i minus 4i negative 5 and 6. Now we're going to first solve for 4a plus 3b. As you can see, we actually have scalars here. We have 4, which is a scalar that's going to be multiplying the vector A. Then we have 3, which is a scalar that's going to be multiplying the vector B. So for 4a, we're going to have 4 times the vector A. Now remember, the 4 is going to be multiplying each of the individual components. 4 times negative 1 is negative 4. 4 times 2 is 8. And 4 times 3 is 12. Then where we have 3b, we're going to have 3 also multiplying each of the individual components in B. So we're going to have 3 times 4, which is 12. 3 times negative 5, which is negative 15. And 3 times 6, which is equal to 18. Now for 4a plus 3b, we're going to now be adding up these new column vectors, the column vector for 4 and the column vector for 3b. Now remember, we're going to be adding each of the individual components. Negative 4 plus 12, which is equal to 8. 8 minus 15, which is equal to negative 7. And 12 plus 18, which is equal to 30. And that's the answer for 4a plus 3b. Alright, so next we're going to solve for negative 3a minus 2b. Now we also have these as scalars right here. Now negative 3 times negative 1 is going to be positive 3. Negative 3 times positive 2 is going to be negative 6. And negative 3 times 3 is negative 9. Then for negative 2b, we're going to have, now because of the negative here, we're going to have this as negative. So negative 2 times 4 is going to be negative 8. Negative 2 times negative 5 is going to be positive 10. And negative 2 times 6 is going to be a negative 12. So therefore, negative 3a minus 2b is going to be equal to the sum of actually these two values. So we're going to be basically adding them up. The reason we can add them up is because this negative has already been multiplied inside. So we're just going to be adding up this and that. So 3 plus negative 8 is basically 3 minus 8, which is going to be negative 5. Negative 6 plus 10 is going to be a positive 4. Then negative 9 plus negative 12 is going to be a 21. Alright, let's look at question number 2. Given A is equal to 2i plus 3j plus 4k and B is equal to 5i plus 6j plus 7k, determine the product of the vectors. Now we have this, we're going to put it in column form. We're going to have A being equal to 2, 3, and 4. Then B shall be equal to 5, 6, 7. Now to get the product, A times B shall be equal to, remember we're going to have each of the individual components multiplying each other, and then we're going to sum them up. So we're going to have this times that, this times that, and this times that. So we're going to have 2 times 5 plus 3 times 6 plus 4 times 7, which shall be equal to 10 plus 18 plus 28, and the answer shall be equal to 56. So that's the product of the two vectors A and B. Now let's look at the magnitude of a vector. Now this is the length of the line representing the vector. The magnitude of a vector, say A, is written as, so we're going to have some vertical bars surrounding the A. So this is actually how we represent the magnitude of a vector. We're going to have some vertical bars around it, which is sometimes called modulus of A. Now the magnitude must be only a positive value. Take note of that. So this is very important. We can never have a negative value for magnitude. Let's look at some questions. We're being told to find the magnitude of A, which is equal to xi plus yj plus zk. So this is actually a 3-dimensional vector. Alright, so the magnitude of this vector A is actually going to be found by taking the square root of the sum of the squares of its components. So what are its components? The components are x, y, and z. So we're getting the sum of their squares and finding the square root of that sum. So this is the magnitude of A. Let's look at another example. We're being told to find the magnitude of B, which is equal to 3i plus 2j minus 6k. Now magnitude of B shall be found from, it's also the same as the sum of the magnitude of the squares of its components. So we're going to have 3 squared plus 2 squared plus, now we have a negative 6 here because it's going to be a negative, so go also square that. Then we're going to have 9 plus 4 plus 36. Now the sum of the squares is equal to 49, and the square root of 49 is 7. So we're going to have the answer as 7 units. Since we are finding the length of the vector, we're going to need to have units. So we're going to leave it as 7 units. Alright, next let's look at a unit vector. A unit vector is a vector whose magnitude is 1 unit. A unit vector can be obtained from any vector by dividing the vector by its magnitude. The symbol A with a heart denotes or represents the unit vector of A. So to find the unit vector of A, we're going to have the vector A dividing its magnitude. And that's the formula. Let's look at an example here. Given that A is equal to 4i minus 12j minus 3k, determine the value of, so we have A with vertical bars, that represents the magnitude of the vector A. Then we've been told to hence find A, so we have A with a heart, so that means we are going to need to find the unit vector of A. So we're going to need to first find the magnitude of A. Now remember that we find the magnitude of A by finding the square root of the sum of its components. So we have its components. So the magnitude of A shall be equal to the square root of 4 squared plus negative 12 squared plus negative 3 squared. Now the sum of the squares shall be equal to 169, and the square root of 169 is 13 units. Now that we have the magnitude of A, we can now also find the unit vector. Alright, now that we have the magnitude of A, we can now find its unit vector from this formula. So we're going to have A divided by 13. Now this can be represented as 1 over 13 times A, because we're actually dividing. So we know what the vector A is. We're going to put it in column vector form as 4, negative 12, negative 3. So the unit vector is basically 1 over 13 times that column vector of A, and that's the answer. Let's look at another question. We're going to find the magnitude of the vector 3, 4, 6, and then write down a unit vector in the direction of 3, 4, 6. Now one thing we've been given is the vector, but in column form. So we're going to let A be equal to 3, 4, 6. Now we know to find the magnitude of the vector A, we're going to need to find the sum of the squares of its components. So we're going to have 3 squared plus 4 squared plus 6 squared, and then we're going to find the square root of the sum. So when we sum these up, we're going to have 61. So therefore the magnitude is the square root of 61 units. Now to find the unit vector of A, it's also going to be found from this formula. So we're going to have A divided by square root of 61. Of course, this is basically the same as 1 over square root of 61 times the vector A. So this can be written this way. So we're going to have the column vector of A 346 multiplying 1 over square root of 61, and that's the unit vector. So next we're going to learn about the dot or scalar product of vectors. Consider two vectors. A is equal to A1, A2, A3 in column vector form, and B is equal to B1, B2, B3. So these are the components of the two vectors. Then the dot product of the vectors A and B is written as A dot B, and this is defined as A dot B is equal to, so we're going to have the magnitudes of the two vectors multiplying each other times cos theta, where A dot B is the same as the components or the column vectors multiplying themselves of each of the two vectors. Of course, this can be represented this way. Remember what happens whenever we were multiplying two different vectors. We would have the two different components multiplying themselves, and then we actually sum up the sum of the products of each pair of components. That's why we have A1 B1 plus A2 B2 plus A3 B3. Then of course we know that the magnitude of the vector A is the sum of the squares, is actually the square root of the sum of the squares of its components. Then the magnitude of B is also the sum of the squares of its components. And then theta is going to be the angle between vectors A and B. Let's look at a question. Find the angle between 3, -2 and 1, 7. So these are actually these are vectors, but these are actually two-dimensional ones. So this means we're only dealing with I and J, because we only have the X and Y components given. So we're going to let A be equal to 3, -2, and then we're going to let B equal to 1, 7. So from this knowledge of dot or scalar product, so this is the formula, we can actually place everything into the formula. So remember, we're finding the angle between them. So that means we're actually looking for the value of theta. So on this side, we're going to have this times that being equal to this and that. So remember, this is the magnitude of A, this is the magnitude of B times cos theta. So this is what we're going to have. So we're going to have this times that being equal to the product of the magnitude of A and magnitude of B times cos theta. So on the left hand side, remember what happens for the multiplication of vectors. So we're going to have 3 times 1 plus -2 times 7 being equal to 3 squared is 9, 2 squared is -2 squared is +4, 1 squared is 1, 7 squared is 49. So we're going to have square root of 13, square root of 50 cos theta. So here we have 3. So -2 times 7 is actually -14. So we have 3 minus 14. 3 minus 14 is -11. And then we know from the knowledge of surds that when we multiply this to this, it's actually basically the same as putting them in the same square root. So it's 13 times 50. Square root of 13 times 50, which is 650. So when we make cos theta the subject, cos theta shall be equal to -11 over the square root of 650. Then we're going to make theta the subject. So theta is going to be equal to cos inverse of -11 divided by square root of 650. Now here, when you place this into your calculator, we're going to get -0.431, and cos inverse of that is going to be equal to 115.56 degrees, and therefore that's the value of theta. So now we have the angle between the two vectors A and B. Let's look at question number 2. Calculate the dot product of the vectors -6, 8 and 5, 12. So we're going to let A be equal to -6, 8, B shall be equal to 5, 12. So B represents one column vector and A represents the other column vector. So from the knowledge of the formula of dot scalar product, this is what we're going to have. So we're going to place everything within. as you can see. Alright, so we're going to do the same thing as before. We're going to first find the value of theta. So now this is what we're going to have. So on this left hand side, we're going to have negative 6 times 5 plus 8 times 12. So here we have the magnitude of a, magnitude of b times cos theta. So negative 30 plus 96 is 66. So here we're going to have square root of 100 times square root of 169. So we're going to have 100 times 169 from the knowledge of SADS. So 100 times 169 is 16900. Then square root of 16900 is actually 130. So making cos theta the subject, cos theta shall be equal to 66 over 130. And then we're going to make theta the subject. Theta shall be equal to cos inverse of 66 over 130. Of course, 66 over 130 in decimal form is approximately 0.508 rounded 3 decimal places. And then we're going to get this by pressing into our calculator. We're going to have theta being equal to 59.49 degrees. So now we know the angle between the two vectors, but we've been asked to calculate the dot product of the vectors. So what we want is the dot product represented. So that means what we're looking for is a dot b. So what is a dot b equal to? So that's what we need. Now we already know that this times this gives us this answer, of which it's actually 130. So that means basically we're going to have this dot that being equal to 130 cos. So it's like we're going to place everything back into the original formula. So we're going to have 130 cos 59.49 degrees, and that's the dot product of the two vectors. Question number 3. Given the coordinates p, it has 2, 3, negative 2, q, 1, 4, 2, and r, 3, 1, negative 2. Find the angle between PQ and QR. So how do we work out such a number? First of all, we need to find PQ and QR. Now, to find PQ can be found from getting OQ minus OP, since we already have the values right here. Now at OQ, since we have this coordinate here, so now just remember this. If coordinates at Q are 1, 4, 2, that means that Q, small q, is equal to 1, 4, 2. Okay? Just remember this, that whenever we say coordinates of Q are that, it also means that either small q, or you can actually represent it this way. That means, let me write this as O. It means that OQ or small q shall be equal to 1, 4, 2. And it's actually the same for this also. So since P is 2, 3, negative 2, it also means that OP is 2, 3, negative 2. And also small p shall be equal to the same column vector 2, 3, negative 2. So that also means that for capital R, if at capital R the coordinates are 3, 1, negative 2, it means small r is equal to 3, 1, negative 2, and that's also the same value for OR. Okay, so just take note of that. So now to find PQ can be found from OQ minus OP. That's how we find PQ. So we're going to have 1, 4, 2 minus 2, 3, negative 2, which is actually the value of OP. And the answer shall be negative 1, 1, and 4. And also going to find QR. Now we're going to find QR from OR minus OQ. So we're going to have it this way. So we're going to have 3, 1, negative 2 minus 1, 4. 2 shall be equal to 2, negative 3, negative 4. So now that we have PQ and QR, now we need to find the angle between them. And of course, we can find the angle between them from dot product. So from dot product, we're going to have PQ dot QR is equal to the magnitude PQ and the magnitude QR times cos theta. So we're going to place everything into the formula, and we're going to first find, so what we're targeting is to find theta. So when we do the calculations, do the math, we're going to end up with square root of 18 times square root of 29 cos theta. Then on this left hand side, we're going to have negative 2 minus 3 minus 16. So we're going to have minus 21 being equal to 18 times 29, the square root of them. So 18 times 29 is equal to 522. So when you make cos theta the subject, cos theta shall be equal to negative 21 over the square root of 522. Then making theta the subject, theta shall be equal to cos inverse of negative 21 over square root of 522. Of course, press this in your calculator and you're going to have some value that's approximately negative 0.019, and cos inverse of that value is 156.8 degrees. So therefore, the angle between PQ and QR is 156.8 degrees. Let's look at another question. If the vectors 5i minus lambda j plus k is perpendicular to the vector 2i plus 3j minus 4k, find the value of lambda. Now this is actually very, very important. We're being told that this vector is perpendicular to that vector. So that basically means that the angle between the two vectors is 90 degrees. That's very important to note. So that means we have the value of theta already. So we know what theta is. If they're perpendicular to one another, then the angle between them is 90 degrees. So that means that from dot product, for perpendicular vectors, we're going to have a 0 on this other side. And how do we get a 0? That's very easy. Remember that if we have a dot b is equal to, so this is how we understand it. So we're going to have cos theta. But remember that for perpendicular vectors, theta is 90. Now on my calculator, cos 90 is 0. And then 0 times the product of these two is still 0. So that means that no matter what you do, the value on the right hand side will always be 0. So that basically means we're going to have this vector dot this vector being equal to 0. So that means we can now use this knowledge to actually find the value of the lambda. So we're going to have 5 times 2 plus negative lambda times 3 plus 1 times negative 4, all being equal to 0. 5 times 2 is 10, negative lambda times 3 is negative lambda, and then 1 times negative 4 is negative 4. So we're going to have to make negative 3 the lambda the subject. So 10 minus 4 is 6. So we're going to take this 6 to the other side and it's going to become a negative 6. So dividing both sides by negative 3, we're going to have lambda being equal to 2. And that's the value of lambda. Question number 5. The points A, B, C have position vectors. A is equal to 5i plus 3j plus 2k. B is equal to 2i minus j plus 3k. And C is equal to 7i minus 3j plus 10k respectively. Show that the angle ABC is a right triangle. So the first thing we're going to do is we're going to need to represent the triangle. Now, this is very important. We're going to be presenting the vectors with small letters. So the lowercase letters A, B, and C are placed opposite their respective vertices A, B, C. Okay? So this is the triangle A, B, C. As you can see, if the vector A, now let's first place the vectors. So this is where we're going to have the angle theta. So we're looking for the angle at ABC. So we're looking for this angle right here. So we're going to place the vector A, B, and C. So we place A opposite the vertex A, capital A. Then we're going to place this small b opposite the vertex B. Then we're also going to place a small c opposite the vertex capital C. As you can see, this is actually very basic. If we know that we have if the vector A is 5i plus 3j plus 2k, it basically means that the coordinates at capital A are 5, 3, 2. So it's actually straightforward. And then likewise for each of the other values. Now the reason we don't have arrows is basically because of the position vector. Now this is very important. In triangle ABC, the origin itself doesn't appear, so we actually don't mention it. So it's just a reference base point that allows you to calculate and compare positions and directions in space. And then we always know that that origin is always at the coordinates 0, 0, 0. So a position vector of a point tells you how far and in what direction that point is from the origin. But in this case, in the triangle, we actually don't know where it's actually positioned. So actually what that means is we're not going to put any arrows. So we only put the arrows to show the direction of the vector when we know the origin. According to the question, we're being asked to show the angle at A, B, C. So that means the angle at B is a right angle. So we're being sure that the angle ABC is a right triangle. So that means that we are assuming that at B that we're going to have 90 degrees for theta. So the assumption is that triangle ABC is right triangled at B. So it means that the angle between AB and BC should be 90 degrees. And that means, now remember that from dot product, this means that the vectors BA and BC are perpendicular. Okay, now that's very, very important. When we talk about the vectors in this case, let's always compare from the starting point right here. So we're going to be looking at it from here, and that's very, very important. You're also always going to have to look at the vectors from B to C and then from B to A. So from dot product, BA dot BC shall be equal to BA BC, their magnitudes, times cos theta. So now we all just need to confirm that theta is 90 degrees. Now to find BA, we're going to find BA from OA minus OB. So we actually know what small a is. Remember that small a is basically the same as OA. So that's going to be 532 minus OB, which shall be equal to 2, negative 1, 3. And this shall be the answer. So let's also find BC. BC can be found from OC minus OB. Now we know what OC is. OC is going to be 7, negative 3, 10. And then OB is going to be equal to 2, negative 1, 3. And that shall give us 5, negative 2, 7. Now that we know that, we can actually place them into the dot product. Then on the left hand side, we're going to actually find so we're going to sum up the product of each of the components multiplying each other in pairs. And then on the right hand side, this is actually what we're going to have. We're going to have the square roots of the sums of the squares of the components. So when we narrow this down, 15 minus 8 minus 7 shall be equal to 0. Then 26 times 78 shall be 2028 cos theta. Now when we make cos theta the subject, we're going to have 0 divided by the square root of 2028, which is basically 0. So we're going to have cos theta being equal to 0, and then theta is cos inverse of 0, and cos inverse of 0 is 90. So now we've actually confirmed that this is actually right triangle. So therefore the angle between ABC is 90 degrees. So we've actually confirmed it to be true. Let's look at a question from UNEB 2017, and this was question number 5. So according to the question, we were told that the vertices of a triangle are P 4, 3, Q 6, 4, and R 5, 8. So we're being told to find the angle RPQ using vectors. So the first thing we want to do is to draw the triangle. So we have point P, point Q, and point R with each of their coordinates. Now remember, small p can be placed opposite the vertex capital P. There we can place the Q and the R. Now remember that this small p is also what we represent as OP. This is also what we represent as OQ. And this is also what we represent as OR. Now from dot product, remember we're dealing with so we've been told to find the angle RPQ. That means we're dealing with the angle at this point. So that means we're actually looking at it this way. So it means we're going to be looking at the vectors P, Q, and PR. So that's why we have PQ times PR is equal to the So we're going to need to find the magnitude of PQ times the magnitude of PR times cos theta. So now PQ can be found from finding Q minus small p. So this is the same as OQ minus OP, of which the answer shall be 2, 1. Then PR can be found as OR minus OP, which shall be equal to 1, 5. Now placing all these back into this dot product, this is what we're going to have on the right hand side. We're going to have this, and then 2 times 1 is 2, 1 times 5 is 5, 4 plus 1 is 5, 1 plus 25 is 26. So 2 plus 5 is 7, 5 times 26 is going to be equal to 130. Now making cos theta the subject, cos theta shall be equal to 7 over square root of 130. Theta shall be equal to cos inverse of 7 over the square root of 130. Now theta shall be equal to 52.13 degrees. So therefore the angle RPQ is 52.13 degrees, and that is the answer. Let's look at another question from UNEB 2002, and this was question number 2. So being told that the vertices of a triangle are P 2, negative 1, 5, Q 7, 1, negative 3, and R 13, negative 2, 0. Show that the angle PQR is equal to 90 degrees. So represent this on a triangle. We have the point PQR with their coordinates small p, small q, small r, and that's the angle because we're actually dealing with the angle at Q. So from dot product, we're going to be finding QP times QR. So that's how we have it that way. Now QP can be found from OP minus OQ, which is 2, negative 1, 5 minus 7, 1, negative 3. The answer of QP shall be negative 5, negative 2, 8. Then QR shall be equal to OR minus OQ, which shall give us 6, negative 3, 3. So we're going to place all those back into the dot product formula. And then this is what we're going to have. Now negative 30 plus 6 plus 24 shall be equal to 0. Then 93 times 54 is 5022. Now cos theta shall be equal to 0 because 0 divided by this is actually 0. Then theta shall be equal to cos inverse of 0, which is 90. So we've actually confirmed it that the angle between PQR is 90 degrees, and that's the answer. Alright, so next we look at the cross product of vectors. Now consider two vectors. A is equal to that, so those are its components. So these are 3 dimensions, and B is equal to that. Then the cross product of the vectors A and B is written as A cross B, or A times B, as you can see there with that X sign. And this is defined as A times B is equal to A B sine theta. So now instead of having a cos theta, we now have a sine theta, and we're also multiplying the magnitudes of A and B. So you can see we have a determinant representation of the vector product A, B. So to find the actual components of A, B, their vector product, we use the determinant but with the unit vectors I, J, K, where we can actually expand this. We can expand the determinant. Then as you can see, we're going to have I into A2, B2, A3. So it's basically like this shall be handling these 2 values. This shall be multiplying these 2 values here. J shall be, so we're going to have a minus J. J shall be multiplying this and that. Then K shall be multiplying this and that. I think that's the best way of understanding it. So we're going to have I minus, then a plus. As you can see, we've actually expanded the determinant, and that's what it's going to give us. So a determinant is a scalar value that is calculated from a square matrix, as you can see right there. As you can see, we're going to have like a square matrix. So I into A times B3 minus B2 times A3. Then we have this minus sign right here, J into A1 times B3 minus B1 times A3 plus K into A1 times b2 minus b1 times a2. And then we definitely remember how to find the magnitude of a. That's the formula, and that's also how we find the magnitude of b. And then theta is the angle between the vectors a and b. Now there is something very important to note. The determinant actually gives the components of a vector that is perpendicular to both a and b. So crossing two vectors gives a vector normal perpendicular to both of them. Let's look at a question. We're being told to find the vector c, which is normal to the vectors a, which is 5i plus 3j plus k, and b is equal to I plus 2j plus 2k. So remember that that vector which is normal can be found by getting the vector product, okay, using cross product. So this is what we're going to find. So a is going to be equal to the vector product. Then as you can see, we're now going to expand the determinant representation of that vector product. Then this is what we're going to have. So now expand it further, we're going to have 3 times 2, 2 times 1, and I think you get the basics of it as you can see in the formula that we got before. And then this is what we're going to have. We're going to have c being equal to 4i minus 9j plus 7k, and that is the vector which is normal, or this is also the vector that is perpendicular to both vectors a and b. That means that when you find the angle between this vector and any of these two vectors, you should actually get 90 degrees. That should also mean that the dot product of this vector and any one of these is actually going to be giving us theta being equal to 90 degrees. Now calculate the cross product of the vector. So these are the vectors we've been given. So we're going to let a be equal to the first column vector 2, 3, 4. Then b is going to equal to the second column vector 5, 6, 7. So now we're going to get the vector product. So this is the determinant representation. We expand it. Then when we expand it further, this is what we're going to have. And then when we simplify this further, we're going to have negative 3i plus 6j minus 3k. And that is the answer. So therefore, negative 3i plus 6j minus 3k is the vector perpendicular to the column vectors 2, 3, 4, and 5, 6, 7. Now let's look at what we call the area of a triangle. Now one of the amazing things about cross product is it actually has some applications. And one of the applications is you can use it to find the area of a triangle. To find the area of a triangle using vectors, especially in 3D space, we use the cross product of two vectors representing two sides of the triangle. So for example, if this is our triangle A, B, C, then remember these are actually the vectors on the sides. We can get the area from, remember area just from general knowledge, a half times base times height. Now in this case, area shall be equal to, so you can have area be equal to a half a times b sine c. So I think in each of the cases we can actually pick a side, then we pick the vectors that are actually adjacent to it. So area, if we are going to have area, let's imagine we're going to have this vertex capital C. So the area shall be a half a times b sine c. And then remember, this actually represents the cross product. So this can be written as the vector product, A and B. Then similarly, if we pick this side A, we can say the adjacent vectors are B and C. So we can have area is equal to a half BC sine capital A. Then from cross product vectors, formula we can actually have a half of the vector product B and C, and that's another formula. Then also likewise, if we pick the vertex capital B, we can have area is equal to a half times A, C, which are the adjacent vectors to this, and then sine capital B, which can also be represented as the vector product of A and C, and that's the third formula. So this is actually how we find the area of a triangle. Let's look at some questions. We've been told to find the area of the triangle with vectors 3i minus 4k. 2i minus j plus 2k, and 7i plus 4j minus k. Let's first draw the triangle ABC. As you can already see, if we were to find the points AC, let's actually first find the points AC. AC can be found from OC minus OA, which is going to give us that value 713. Then we can also find AB, which is going to give us OB minus OA, which is 2 negative 4 6. So in this case, we've actually chosen one of the sides that we're actually going to deal with. So we've actually chosen to so basically in this case, since we've chosen AC, it actually basically means we've chosen to use B here. So remember, we're going to have a small b here, we're going to have a small a here, then we're going to have a small c here. So basically what we've done is we've decided to use the formula for area. So remember, area is equal to a half. So we've actually chosen to have the side. Okay, since we've chosen AC and AB, we've actually chosen this side right here. So we've also chosen this formula, BC sine A. Of course, B is going to be representing AC, then C is representing, C is representing AB. So that's actually what we are doing. It's actually basically the same thing. So this is exactly what we get from here. Okay, and sine A. And of course, remember that this is basically the same as B, and that is actually what we actually have right here. So for A vector product of AC and AB, remember this formula, we're actually going to use the determinant representation, then we're going to expand it. So when we expand it further, this is what we're going to have. Then when we multiply the values, we're going to have the vector product being equal to 18i minus 36j 30k. And that is the value for the vector product. Now we need to find the magnitude of that vector product, as you can see. So the magnitude is going to be this 18 squared plus negative 36 squared plus negative 30 squared, which shall give us 2520. So the square root of 2520. Now remember that area is equal to a half times this value right here, and that is our answer. So whatever I get from a half times this value is our answer. We can actually leave this in full so that we don't need to write many decimal places. So this is actually correct. So therefore the area of the triangle is a half times the square root of 2520 square units. Let's look at another question. 3 points PQR have coordinates P 425, Q 3, negative 1, 6, and R 142. Show that PQR are vertices of a triangle, and hence find the area of the triangle PQR. So now we have two things to do. We have to first prove that these are vertices of a triangle PQR, and then we are supposed to find the area of the triangle. So how do we prove this? Let's first sketch the triangle. These are the different points of the triangle, but just for knowledge, remember that we're going to have the small p right here. So this is going to be the small q, OQ. Then this is going to be where we have the small r. Now for triangle proof, for a triangle there is actually a rule. So for a triangle, PQ plus QR plus RP should actually be equal to 0. That's also like saying small p plus small q plus small r should be equal to 0. So that's actually supposed to be true. Now let's first find the value of PQ. We're going to get PQ from OQ minus OP, and that's going to be this, and the answer shall be negative 1, negative 3, positive 1. Then QR shall be equal to OR minus OQ shall be negative 2, 5, negative 4. Then lastly, RP shall be equal to OP minus OR, which shall give us 3, negative 2, 3. Now remember that this is supposed to be true, so we're going to sum up the values that we've actually found, and then as you can see, they give us the answer 0. So now that we actually have a 0 in each of the different components, each one is summing up to 0, so this basically means that PQR is a triangle, and that is the proof. Now to find area of the triangle, remember we're going to use any of the formulas that we've chosen. Now I've chosen to go with PQ times QR. That basically means that I've actually chosen to go with this side here. So that means that I've chosen to use the formula area is equal to a half P R sine Q. So this is basically the same as half P which is basically the same as So I've just done this so that you actually understand, but you can actually use any of the sides that actually match with the formula. Alright, now let's first solve for PQ, the vector product of PQ and QR. So now we're also going to first arrange and find the determinant. So this is the determinant representation of that vector product. Then when we expand it, it's going to give us 7i minus 6j minus 11k. Now next we need to find the modulus of that vector product. 7 squared plus 6 squared plus 11 squared, which shall be equal to 206, the square root of 206. So next, the area of the triangle therefore is a half times this value square units. So therefore that is the area of the triangle, and that's the answer. Next, let's look at a question from UNEB 2018, and this was question number 9. The question says the position vectors of the vertices of a triangle are O, R, and S. Now this is very important information, where O is the origin. Show that its area A is given by 4A squared is equal to R squared S squared minus bracket R dot S squared. Hence find the area of the triangle when R is equal to 3 and S is equal to 1, 4. So first thing we want to do is we're going to sketch the triangle. Now we've been told that this triangle actually has an origin O. So we're going to have the point S and the point R. So we actually have to place those in. Then we're going to put the small r and the small s. Now since we actually have an origin, we can actually have the directions, or the arrows that represent the directions. They're going to start from the origin. So this is OR and this is OS. Now we know that area can be found from OR times RS. So basically we've actually chosen to use this point right here. So this is basically like saying area is equal to a half r small s sine capital O. So it's basically the same thing, but we've actually gone straight forward and already placed it in its vector, in its cross product form, vector product form with the magnitude signs. So this is actually what we're going to have. So this is the formula we're going to be using in this case. Why have we chosen to do that is because we know the vector OR and we know the vector OS. Now since we don't know anything at RSS, we're going to be focusing on these two sides. But this is actually enough information to actually prove this. So this is the proof we are looking to show. Now this can be repeated as R cross X. So remember, it's actually the same thing. Now we know that if we multiply a 2, now we actually want it to look like this. But the only way of eliminating this a half because there's actually no half in the proof, is we actually have to multiply a 2 on both sides. When you multiply a 2 here, we're actually going to have a 1, then we're going to have 2a on this side. Now next, for us to actually get this 4a, we're actually going to have to square both sides, because we actually see a squared on both sides. That's actually the next step. So when you square both sides, we now have 4a squared. So we now have what is actually on the left hand side, and then now this is a square this side. So now I actually have to prove that this side will actually look like what we actually have right there. Now from formula of cross product, we know, let's actually deal with this side alone. Let's deal with r, the vector product of r and s. So this can be written as the magnitude of small r times the magnitude of small s sine theta. And then this can be written this way. So now when we bring the squared in, we're going to have this magnitude of r squared, this magnitude of s squared, and then sine squared theta. But we also know from trigonometry that sine squared theta is actually the same as 1 minus cos squared theta. Now that we know this, we're going to use knowledge from formula of dot product. Now we know from the formula of dot product that r dot s is equal to the magnitude of r times the magnitude of s cos theta. So we're actually going to use that knowledge. Now let's make cos theta the subject here, because we actually want to place this back in. Cos theta shall be equal to r dot s divided by the product of the magnitudes of r and s. So we shall now have this. So we're now just putting this back where we actually have the cos theta, cos squared theta. Now this is what we're actually going to have next. So now we can actually we can solve these fractions. So we're going to have this as the denominator. So because this is actually going to be equal to 1. So this divided by 1 shall be equal to this. So this times 1, we're going to have it at the top, minus, then this divided by this is 1. 1 times this at the top, we're just actually going to remain with it just the way it is. Alright, so next we're going to continue expanding. When we multiply this in, this will cross with what we actually have there. And then what we shall remain with is 4s squared is equal to the square of the magnitude of r this times the square of the magnitude of s minus r dot s bracket squared. And that is the proof they were asking for. Now let's look at the hence part. Now we know that the magnitude of r is going to be given this way. From the values we are given, we know what r is. We're going to have 2 squared plus 3 squared, which is 4 plus 9, which is got the square root of 13. Then small s is going to be, so we're going to sum up the squares of its components and find its square root also. So we have 1 plus 16. So the answer is, of the magnitude of small s, is the square root of 17. So therefore, r dot s shall be equal to that. Now we're going to be using this formula here to actually find the eventual area. So r dot s can be represented this way. So we're going to have 2 times 1 plus 3 times 4, which is actually going to be equal to 14. Then we're going to place those values back into our proof. So placing them into our proof, this is what we're going to have. Now remember, we're just going to make a the subject in this proof, and then we're actually going to have the area. 14 squared is 196. So square this and this, and then we'll have that root disappearing. 13 times 17 is 221. So 221 minus 196 is 25. So we have 4s squared being equal to 25. Then when you make s squared the subject, we shall have 25 over 4. Then we're going to find square root on both sides, multiply by the root on both sides. So we're going to have a being equal to the square root of 25 over 4, which can be simplified as 5 over 2. So 5 over 2 is 2.5. So therefore the area is 2.5 square units, and that's the answer. Now let's enter a very important part of this section. Now we're going to look at conditions for perpendicular and parallel vectors. Now there are some things we've already confirmed through our study in this section, but we're actually going to do a slight revision of them to just make sure you've actually understood them fully. Now we know that for perpendicular vectors, that suppose we have two vectors A and B and they are perpendicular to each other, it implies that the angle between them is 90 degrees. So we can actually represent it this way. Now from dot product, we've already seen that for perpendicular vectors like this, where we have cos of 90 degrees, where the angle between the two vectors is 90 degrees, remember that cos 90 is 0. So that means A, the dot product of A and B is actually equal to 0. I think we've actually seen that before. It's just that we want to emphasize it for our remembrance. So the whole idea is the dot product of perpendicular vectors is 0. So this is the condition for perpendicular vectors. Now from cross product, let's look at that case also. So if the theta is 90 degrees, we can actually say that sine of 90 is 1. So what that means is we'll actually have a 1 here, 1 times this. So that actually means we have the product of the magnitudes. So that means that in this case, this is the perpendicular, this is the condition for perpendicular vectors when we use cross product. So in perpendicular vectors, the vector product is equal to the product of the magnitudes of the two vectors. Let's look at some examples. Show that A is equal to 3i plus 5j minus 2k and B is equal to 3i minus 3j minus 3k are perpendicular to each other. Now from cross product, actually this is actually very clear. From cross product, we actually already know that this is actually supposed to be equal to that value. Let's use the knowledge of cross product. Now let's first find the cross product of that. This is not the easiest, so of course it would have been easy and straightforward to use dot product, but we can actually use both ways. Let's actually, so this is the determinant expression. Then when we expand it more fully, we're going to have the answer as negative 21i plus 3j minus 24k. And then remember that this is the condition for perpendicular vectors when we use cross product. So for perpendicular vectors, you know that this should be equal to that. So let's actually first find this. Let's find the magnitude of the vector product. So we're going to have square root of 1026. Then now let's actually look at what we have on this other side. So the magnitude of A shall be equal to square root of 38. The magnitude of B shall be equal to the square root of 27. So now we shall have, so on this other side we're going to have square root of 1026 being equal to the square root of 38 times 27, of which we have the square root of 1026 being equal to the square root of 1026 on the right hand also. So since the magnitude of the vector product is actually equal to the product of the magnitudes themselves, therefore A is perpendicular to B. Now that is not the easiest way of proving it, but it actually proves to be true. Let's look at the other way, what I would call the easier way. From dot product, it's very clear that for perpendicular vectors, the vector product should actually be equal to 0. So that basically means get those two vectors, and we're actually going to expand them. 3 times 3 is 9, 5 times negative 3 is negative 15, and then negative 2 times negative 3 is 6. So when you actually sum these up, we shall actually have a 0, and therefore this proves that the vector A is perpendicular to vector B. So these two vectors are perpendicular to each other. I personally think I would actually use the way of dot product if I wanted to prove this, but I hope this makes sense. Let's look at a question from UNEB 2005, and this was question number 4. So the question was that given the vectors AI minus 2j plus k and 2AI plus aj minus 4k are perpendicular, find the values of A. Now I think we shall use the knowledge of dot product in this case. So we're going to first let P Now you can use any small letters of your choice. The reason I've chosen not to use A and B is because we already have A as unknown, as the value we actually have to find. So we're going to use some different letters to represent the vector. So we're going to let P be equal to A, negative 2, 1. Then we're going to let Q be equal to 2A, A minus 4. So from dot product, it's what we're going to be using. So we've been told that these two vectors are perpendicular. So that means that they should fulfill this requirement, that for perpendicular vectors, P dot Q should be equal to 0, the vector product, the dot product. So that means this should actually be equal to 0. So when we actually expand what we have on the left hand side, we shall have A times 2A plus negative 2 times A plus 1 times negative 4. So we're going to have this being equal to 0. Now for quadratic equations, we're going to actually first factorize out A2. Then we shall have A squared minus A minus 2 being equal to 0. Now for quadratic equations, we shall either have A being equal to 2 or A is equal to negative 1. And that is the, let's say, those are the answers to the values of A. Let's look at a question from UNEB 2006, and this was question number 11, part A. Given the vectors A is equal to 3i minus 2j plus k and B is equal to 1 minus 2j plus 2k, find 1. The acute angle between the vectors. 2. The vector C is such that it is perpendicular to both vectors A and B. Now, I think we remember something, that if we were to find a vector that is perpendicular to both A and B, that basically means we have to find the cross product of A and B. I hope we remember that knowledge, that every time we find the cross product of two vectors, the answer we get is actually perpendicular to both of them. So let's first find the acute angle between the vectors. Let's first deal with part 1. We're going to use dot product for the first one to find the angle theta. So we're going to use dot product. So putting it in the formula, let's expand. So on the left hand side, this is what we shall have. This is what we shall have on the right hand side. Simplify it further. So we're going to have 9 being equal to 3 times the square root of 14 cos theta. Make cos theta the subject. Then theta shall be equal to cos inverse of 3 over square root of 14. Put that in your calculator and you shall have theta being equal to 36.7 degrees. Now, to confirm your answer is true, it should be an acute angle, which is an angle less than 90 degrees. And since our 36.7 degrees is less than 90, I believe we are right. So this is the answer you should get. Now for part 2, remember that a vector perpendicular to both vectors is given by their cross product. So C shall be equal to the vector product AB. So we're going to actually express this in a determinant representation. Then we're going to expand it. Alright, so when we expand it further, this is what we shall have. We shall end up with C being equal to negative 2i minus 5j minus 4k. And therefore the vector C, which is perpendicular to both vectors A and B, is negative 2i minus 5j minus 4k. Let's look at parallel vectors. Now suppose two vectors A and B are parallel to each other. It means that the angle between them can be 0 degrees if they are like parallel vectors, okay? Or 180 degrees if they are unlike parallel vectors. So there are two ways of expressing parallel vectors. We can have those that are like and those that are unlike. Now, this is an example of like parallel vectors. Now, like parallel vectors face the same direction. As you can see, the vector A and B are all in the same direction. And then we can have unlike parallel vectors. So these are actually parallel to each other, but they face different directions. And the angle between them is 180 degrees. Now, from dot product, A dot B, now remember for the case of where they are actually like parallel vectors, that means that theta is going to be equal to 0 degrees. But remember that cos of 0 is 1. So that means that for like parallel vectors, the dot product A dot B shall be equal to the product of the magnitudes of A and B. Now, also from dot product, if we're dealing with unlike parallel vectors, that means we have cos 180 to deal with. Now cos of 180 degrees is -1. So therefore, A dot B shall be equal to the negative of the product of the magnitudes of A and B. So that's actually how you know if they are actually in the same direction, if they are parallel but in the same direction, or if they are parallel and in different directions. Let's look at a question. Determine whether the following vectors are parallel or not. I minus 2j plus 3k and -4i plus 8j minus 12k. Now from dot product, this is what we're actually going to have. So these are the two vectors. So this being equal to the product of the magnitudes. Okay. Now if these are equal, if the two values are equal, then they are parallel. So when we expand them, we shall have -56, and the square root of 3136 is actually 56. So you can actually see that the values are actually the same, though we actually have a negative on one side. So that actually means that these are actually truly parallel, but they are unlike parallel vectors. That means they're actually facing different directions. So this implies that the two vectors are unlike parallel vectors. So the condition is actually true. So when you actually show that they are either unlike or unlike, it actually shows an intelligent mathematician that you've not only confirmed that they are parallel, but that you are also aware of the direction of the two vectors. Let's look at another question. Determine whether the following vectors are parallel or not. I plus 12j plus 3k and 2i plus 6j plus 12k. So from dot product, we're actually going to try to prove this. So we have 110 being equal to the square root of 28,336. And we can see that that square root is giving us 168.33. And these are actually not equal. So this implies that the two vectors are not parallel. Alright, so next we look at another way of looking at parallel vectors. Now, two vectors are parallel if one of them is a scalar multiple of the other. Multiplying or dividing a vector by a scalar only changes its magnitude but leaves the direction unaltered or unchanged. For example, if A is parallel to vector C, then A is equal to lambda C. And that's the formula, where lambda is a scalar, a real number, or a constant. So in some books they'll call it the constant of proportionality. Now actually I want to explain this in terms that anyone can understand. Now I think we've made it clear two vectors are parallel if they point in exactly the same direction or opposite directions, as we've seen before, because we've talked about those that are like parallel vectors and those that are unlike parallel vectors. But now we want to also introduce a new concept. Even if one of the vectors is longer or shorter, as long as they both go the same way, they are still parallel. So mathematically we say that one vector is a scalar multiple of the other, where lambda is a number that stretches or shrinks the vector. But I want to explain it in a way that you can easily understand. For example, we may have a vector like, now let's consider this that we have here. So we can say A is equal to, instead of lambda, let's say 3c. Now you should know what this means. So when you write it this way, it means that A is actually parallel to C, but C is actually shorter. Now in this case, this is like saying that C is 3 times, or actually it's like saying A is 3 times longer than C. That's why you have to multiply a 3 to the C to actually get the length of A. And actually this can also be changed and written this way. So this can also be written as C is equal to 1 over 3 A. And this is actually the same thing. This still means that A is still 3 times longer than C, or that C is a third of A. So in all these cases, one is a stretched or shrunk version of the other. Okay, now as we've seen before, if lambda is positive, that means they point in the same direction. And if lambda is negative, it means they point in opposite directions. And lambda, as we said, is the constant of proportionality. Let's look at some questions. Given b is equal to 3i plus 9j plus 2k and d is equal to 9i plus 27j plus 6k, prove that b and d are parallel. Now, if b and d are parallel, then b must be equal to, there will be some constant of proportionality times d. So there will be a scalar multiplying d if these are to be parallel. Now looking at d is equal to that, I can see that I can actually factorize out a 3, and then I'll have d is equal to 3 times into bracket 3i plus 9j plus 2k. But we've seen that b is equal to 3i plus 9j plus 2k. So we can have d being equal to 3b. So that means we've actually substituted this value here with b because we know the value of b. And since that is true, we can also see that this likewise can also be written as b is equal to a third of d. This proves that b is equal to lambda d, where lambda is equal to a third. And of course, this can also be said, so this is just one way of saying it. So we can also say that d is equal to lambda b, where lambda is 3. So it's like in different cases, but we've actually chosen to represent it using this alternative that b is equal to lambda d, where lambda is equal to a third. You could also say that this proves that d is equal to lambda b, where b is 3. So each of those answers would be correct. So since lambda is equal to a third is a scalar real number, therefore the two vectors b and d are parallel to each other. So this is another way of proving parallel vectors. Alright, let's look at a question from UNEB 2003, and this was question number 11. So let's read it carefully. So it says, in a triangle ABC, the altitudes from B and C meet the opposite sides at E and F respectively. BE and CF intersects at O. BE and CF intersect at O. So taking O as the origin, use the dot product to prove that AO is perpendicular to BC. Then in part B, we're being told to prove that the angle ABC is equal to 90 degrees. And then we're told that given that A is the coordinates 0, 5, negative 3, B is 2, 3, negative 4, and C the coordinates are 1, negative 1, 2. Find the coordinates of D if ABCD is a rectangle. Let's start with part A. Now in part A, it's very important to first sketch the triangle with all the instructions that we've actually been given. So we've actually seen that we actually need to draw a line, a straight line, on each of the sides. So we're going to need to have 90 degrees here because this cuts right in the middle. Okay. So we're going to have 90 degrees on all sides. So we have A, B, C. Then this is going to be a point that we're going to add. We're going to call this point, point G. Then we're going to call this other point, point E. Then we're going to call this point, point F. And that clearly follows the instructions. Now G was not given, but we've just chosen to add it to actually make our what we follow clear, because we've seen that B and C meet the opposite sides. So you see B and C meet so B is meeting the opposite side AC at E, and then we're seeing that F is also meeting, C is meeting this opposite side AB at F. And then we've been told that BE, BE, and CE intersect at O. So that means we actually have a point O. Let's first write the vectors. So that means we actually have an origin. So the origin is this point right here in the middle. So that means we're going to have a vector A, we're going to have a vector B, and a vector C. Now, we also know that for AO to be perpendicular to BC, we need to prove that AO dot BC is equal to 0. Now that is the condition. Now which one is AO? AO is this point here. We want to prove that it is perpendicular to BC. For that to be true, we know that this condition actually has to be proved to be true. Now we can actually see some facts that are actually true. We can see that OE, as you can see, OE and OB are actually on the same parallel line. So that means we can actually add that constant of proportionality, that OE is equal to some constant times OB. So that can actually be true. Then we can actually say that we can do the same for OF. OF is here. So OF and OC are actually also on the same. They're on the same. They're all parallel, even if they are opposite each other, OF and OC. But we can actually see that the constant, we can add a different constant of proportionality for them. Let's use this. And then for OG, we can see at OG, which is this, and OA, we can also have a constant of proportionality. So beta OA. Now we can clearly see that OA is equal to small a, OB is equal to small b, and OC is equal to that small c. And then clearly AB is equal to B minus A, because we get AB from OB minus OA, which is B minus A. Then SC is equal to OC minus OA, which is definitely C minus A. And then BC is equal to OC minus OB, which is C minus B. Now you may ask a question, why do we have a 90-degree angle right here? I mean, clearly this is 90 degrees, but why are these also equal to 90? And that is because of the language of the word altitude. We've been told that in a triangle ABC, the altitudes from B and C meet the opposite sides at E and F respectively. Now you should note an altitude is a perpendicular line segment from a vertex of a triangle to the opposite side. It is a straight line and it must be perpendicular with the opposite side. So that is something you should notice about languages. So mathematically, an altitude is a perpendicular line. So that means that these must be equal to 90 degrees. Now BE is the altitude from B to AC. So therefore BE is perpendicular to AC. Now, so from dot product, it will actually mean that OE dot AC should actually be equal to 0. As you can see, OE is perpendicular to AC. So that actually means that these are actually perpendicular to each other. So that actually should also meet the rule of perpendicular vectors. And then remember from our proofs that OE is actually equal to lambda OB. And then we also know that OB can be represented as small b, and then AC can be represented as C minus A. Now we can divide both sides by this lambda, and the lambda will disappear, and we'll be left with B dot bracket C minus A is equal to 0, and this shall be our equation 1. Now also, we know that CF is the altitude from C to AB, so therefore CF is perpendicular to AB. So from dot product, it actually means that OF is perpendicular to AB. As you can see, OF is perpendicular to AB. So that means that OF dot AB shall be equal to 0. So now we're going to have this. Now OF, remember, is equal to lambda of OC dot AB. And then we can actually divide both sides by this, and we're going to end up with C dot B minus A is equal to 0. And that's going to be our equation 2. Now since both equation 1 and equation 2 are equal to 0, it also means we can equate them. So now equating them, this is what we're going to get. So now what we can do is we can bring the values over on this side to the left hand side, and then when we open the brackets, this is what we shall end up having. As you can see, this and this will cancel. Then we'll be left with A dot C minus A dot B is equal to 0. Then what we can see is we can actually factorize out the A. And then it will be A into A dot C minus B. which is equal to 0. And then we now clearly remember that A is represented as OA, and then C minus B can be represented as BC, all being equal to 0. So that means that OA and BC are perpendicular. So hence AO is perpendicular to BC. Now part B of the question says prove that the angle ABC is equal to 90 degrees given that A is equal to that, B is equal to that, and C is equal to that, and then find the coordinates of D if ABCD is a rectangle. So we're going to first deal with the first part of part B, and then in the last part is we are being told if we make it a rectangle. But before we do that, let's first deal with it the way it is in part B. Now this is what we're going to sketch. So we're going to pick out the part that has ABC, and we're going to have the origin. So that's where we have the angle theta, the angle we want to prove. Then we have A, vector B, and vector C. Now from dot product, we know that BA dot BC should be equal to BA BC cos theta. And why is that? We're picking the vectors from this point right here. So we're going to deal with BA and BC since we want to prove this angle right there. I believe you will remember that from what we've been doing at the very beginning. Now to find BA is equal to OA minus OB. And then when we subtract this, we're going to have negative 2, 2, and 1 as the position vector for BA. Now to find BC shall be equal to OC minus OB, which is equal to negative 1, negative 4, and 6. Now substituting into the dot product formula, this is what we're going to have. Then when we solve this, we're going to remain with 0 on the left hand side. Then 9 times 53 is equal to 477. And then when we divide both sides, 0 divided by square root of 477 is 0. So that means cos theta is equal to 0. Now cos inverse of theta is 90. So therefore theta is equal to 90 degrees. The angle between ABC therefore is 90 degrees. Now the last part of the question says find the coordinates of D if ABCD is a rectangle. So in the last part we're going to assume that ABCD is a rectangle. So the rectangle is A, B, C, D. So we're putting those coordinates of A, B, and C, and then we're going to assume that those of D are unknown. Now for a rectangle ABCD, we know that AB should definitely be equal to CD because it's a rectangle. So this side is definitely equal to that side. So that means that OB minus OA, of course to find AB it's OB minus OA, should be equal to, so means to find AB we need OB minus OA should be equal to find DC we need OC minus OD. Then when we put in those values, this is what we shall have. So we shall have XYZ. So we're going to bring this over to this side and take that to the other side. XYZ should be equal to negative 1, 1, and 3. And it's actually as simple as that. So hence the coordinates of D are negative 1, 1, 3. Let's look at the final part of this introduction of vectors. We're going to look at equal vectors. Now vectors are equal if they have the same magnitude and direction. So if A is equal to Pi plus Qj plus Rk and B is equal to Xi plus Yj plus Zk, then A and B shall be equal if P is equal to X, Q is equal to Y, and R is equal to Z. So they should have equal coordinates. Let's look at an example. Given that A is equal to Ti plus 2J plus bracket 4 minus Sk is equal to the vector B is equal to 2 minus S in bracket I plus 2J plus 8K, find the values of S and T. Okay, so we've been told that these two vectors are equal. So we know that A should be equal to B because they are equal. So by comparing directions, we have 4 minus S should be equal to 8. So that means this should actually be equal to that 8. And then we can see that s shall be equal to negative 4. Then we can also see that t should actually be equal to 2 minus s, because this should be equal to that if they are equal. So we'll have 2 minus negative 4. So t is going to be equal to 2 plus 4, because this actually becomes a positive, and then t shall be equal to 6. And those are the values of s and t. Let's look at another question. If p is equal to 4i minus into bracket 2 minus tj plus 9k, and q is equal to 3 minus lambda I plus 3j plus t plus sk are equal vectors, find lambda, t and s. So we know that p is equal to q because we know that the vectors are equal. So by comparing directions, we'll have 4. This 4 is definitely equal to 3 minus lambda. Then lambda shall be equal to negative 1 when we solve it. So we can also have negative 2 minus t shall be equal to 3. So we have negative 2 plus t equal to 3. So t shall be equal to 3 plus 2, of which t shall be equal to 5. And finally, we have 9 is equal to t plus s. 9 shall be equal to 5 plus s, because we now know what t is from here. So making s the subject, s shall be equal to 9 minus 5, and s shall be equal to 4, and those are the values of the unknowns. Alright, we've come to the end of the introduction to vectors. I have an exercise for you. These are numbers I encourage you to try out. I've actually placed the answers for you so you can compare and make sure you're actually on the right track. And I believe that this will actually help you sharpen your knowledge and keep you on track. So this is question number 2, question number 3. Now this is question number 4. Question 5. Question 6. Question 7. Question 8. Question 9. Question number 10. Question number 11. Question number 12. And lastly, question number 13. See you in the next part. Thank you so much for watching today's video. If the video really helped you, feel free to give the video a thumbs up by clicking on the like button. And then if you're new to this channel, I encourage you to join the community by subscribing, and then make sure to hit that notification bell so that you get updated every single time I upload a new video. A new video is coming up. Get ready to tune in. See you in the next video.